Hello, everyone, and welcome back to another episode of Pinnacle Academy. I'm Sanal Patel, the Director of Business Development and Marketing at Pinnacle Ozone Solutions and a chemical engineer. Today's conversation is focused on one of the most critical and often overlooked aspects of ozone system performance: measurement, monitoring, and control. Because no matter how well the system is designed, if you're not measuring the ozone accurately, you cannot control it, optimize it, or even troubleshoot it. So today, we're going to dive into that, and I'm joined by Ron Moody, the Operations Manager of OSTI, representing BMT analyzers, and brings an in-depth experience in ozone monitoring as well as field diagnostic. And then our own truly Tom Chandra, who is the Chief Science Officer at Pinnacle Ozone Solutions, and he focuses on application design, lab design, R&D, and system integration. Gentlemen, thank you both for joining me today.
Glad to be here. Thanks for having me.
So just before we go into depth on the analysis, monitoring, everything, I want to just keep this high level. So Ron, let's start with you. For the individuals who are not familiar, can you give us a little bit of an overview of the BMT analyzers, what they do, how they work, and how they typically fit into an ozone system?
Sure, Sanel, thank you. So all BMT analyzers are UV photometers. So let me first explain what UV photometry is for those who may not be familiar with it. Then I can explain how it works and where the instruments are used in industrial application. So first, what's UV photometry? Well, simply stated, it's a technique for measuring how much ultraviolet light is absorbed by a quantity or sample of ozone. Most people are familiar with the concept of stratospheric ozone and how it protects life on Earth by absorbing harmful ultraviolet rays. Well, UV photometry is just putting nature under a microscope. So science has validated that almost 100% of UV is absorbed by ozone at the wavelength of 254 nanometers. That's the mercury band. So some smart people experimented with this and discovered that the amount of UV absorption by ozone is proportionate to the concentration of ozone and a defined length that the light passes through. So in other words, if we know the length and the pressure and the temperature of a defined space, we can calculate how much ozone is in that space by the reduction of UV from a mercury UV source lamp to a photodiode selected to 254 nanometers. So that's really UV photometry in a nutshell. How does that work? Okay, well, this is illustrated in a graphic that I've provided. You can see on the graphic the UV lamp at the top of the drawing sending light through a defined area, which is called a cuvette, to a photodiode at the bottom. The cuvette is continually moving a sample of ozone through that space, so as ozone increases or decreases, so does the light intensity to the photodiode. So the relationship of ozone concentration and cuvette length is linear, so it can be and has been quantified in a mathematical formula. And that is what we all use for reliable ozone measurement. Now, this illustration shows ozone in gas phase, but I should mention that UV photometry also works for dissolved ozone in water with some restrictions on application, which I'll talk about shortly. And in the picture, you also see a second photodiode. BMT analyzers use this additional sensor with an unimpeded path to the UV lamp to allow the instrument to make automatic adjustments for things like environmental drift in the cuvette or changes to the lamp, the plasma over time. This is called dual beam photometry, and it's really unique to the BMT products, which allows us to automate their performance, and that makes manual adjustments and things like recalibration unnecessary. Now we know what UV photometry is and how it works. Let's talk about application. Because ozone is such a potent oxidizing agent, it has many industry applications. So in food and beverage, for example, ozone is used for surface and container sterilization, food preservation, deodorization. Semiconductor manufacturing uses dissolved ozone in a chemical solution for cleaning silicone wafers and for surface passivation. The pharmaceutical industry uses ozone to create ultra-pure water loops, which they use in their manufacturing process. And there are numerous municipal and industrial water treatment applications which is primarily where Pinnacle Ozone plays. So let's take a quick look at the types of instruments you might see in a typical Pinnacle installation, or really any water treatment process plant. The first measurement point is always the output of the generator. It's going to be the high concentration. So every process is given a target for ozone production, usually somewhere between 7 and 20% by weight. And so what will sit at the outlet to the generator is a high concentration ozone monitor. Here's an example of one I'm touching right here, okay? Usually the pressure from the process is enough to move ozone through the analyzer to where a small sample is made and then destroyed with a catalyst destruct at the end. So this one high concentration analyzers don't require sample gas pumps. So here, just a quick view on the inside, you see the ozone comes in and is a small amount of ozone, usually 3 to 5 liters per minute. And we can throttle back the pressure here internal with this flow meter. It's measured and throttled back here to that level. It is sampled through the cuvette. And here's a picture of the cuvette block, okay? And then comes out and is destroyed, okay? This happens to be an industrial cabinet, NEMA 4X enclosure, weatherproof, and so it has its own zeroing and purging functions. Zeroing is important for an analyzer to keep track of what's happening in the environment, especially environmental drift in the cuvette over time. However, they can also be smaller units. This is an example, the exact same analyzer without the flow meter or the catalyst destruct, which can be external to the unit, although that process can be controlled. This is the type of analyzer Pinnacle Ozone uses in their cabinets. This is a sample of that unit, where simply bringing ozone in here, out here, and measuring it along the way and sending an output signal, 4 to 20 milliamps, 0 to 10 volts, 0 to 1 volt, number of options for that. So with Pinnacle, this actually doesn't need a NEMA enclosure because it sits inside of their cabinetry. So after the high concentration measurement, the second measurement point for us is the residual off-gas. This is an example of an off-gas analyzer, and I'll walk around here to kind of illustrate a couple things. Before I demonstrate that, I will say, though, that the second sampling point in a typical water treatment plant might actually be dissolved ozone along the path where it's being exposed to ozone. This actually isn't a good use for ozone photometry, primarily because there's quite a bit of microbial and particulate matter still in the sample stream. So even though water, H2O, is typically invisible to ozone, turbulent water or water that is polluted actually can distort a measurement in UV photometry, simply because it's reducing light from the light source to the photodiode, as I described earlier. So what we typically will monitor is, in gaseous form, is the off-gas. So there's always a little residual off-gas coming after the process. And why do we measure that? Well, we're going to talk about that a little bit later, but primarily we want to know that had enough dosage to do what it's required to do, which is sometimes disinfection, sometimes odor control. So if we know what we're going into a process with 10% and we see absolutely no off-gas coming out, you can conclude that all the ozone is being destroyed and there may be an underdosing happening. So we use off-gas to actually measure the mass transfer efficiency of the process, okay? So the ozone analyzer is slightly larger simply to accommodate a larger power supply and a sample gas pump. Why do we put a sample gas pump in here? Well, with an off-gas installation, what we're doing is we're typically coming right off of an off-gas header. Here's an example of an off-gas header line, okay? And we take that process gas first, since it's humid gas, we take it first through a dehumidifier to condense any humid gas, drop it back into the process line, and cycle the dry gas into the analyzer for measurement, okay? But to normalize the pressure, we then return that back to the off-gas line rather than sending it to a destruct. Okay, that's the second measurement point. The third measurement point, now this is before the system destruct, off-gas is, we also like to measure after the system destructs. So we call this a vent gas monitor, okay? Where actually if the destruct is doing its job, it's going to be, should be pretty close to 100% destroyed. So this monitor is sampling the emission from the system through the destruct and into the atmosphere. We want to make sure that we're not releasing high quantities of ozone into the atmosphere. So we use an ambient ozone analyzer for that, okay? You notice the ambient ozone analyzer is much, much larger. Well, now we're measuring in the parts per billion versus percentage weight or grams per normal cubic meter. And because now we're looking for parts per billion, remember I said that there's a relationship between the cuvette length, right, and the concentration. You notice that this cuvette length here is much larger. We need a higher volume inside that because we're looking for a much smaller portion of ozone, okay? So ambient ozone analyzers have a continuous duty sample gas pump. It's constantly sampling from a space, just atmospheric, okay? It does have a small catalyst destruct inside the unit, and it is self-regulated in terms of flow, so roughly a liter per minute, and monitored for low flow. The fourth point of monitoring, step back around here, is safety monitoring. And that is exactly the same analyzer used for the vent gas. So we simply install in a space where the ozone generators are a wall-mounted single unit. Sometimes we put two if the space is large enough in there, or multi-channel, to sample continuous duty sampling of various points inside where the ozone generator room is or the ozone piping pathway. Simply doing safety checks is basically leak detection monitoring. So those are the most common application points for ozone monitors in water treatment, and this is largely what you'll see on a Pinnacle ozone installation.
Thank you so much, Ron, for that. So jumping on to Tom for this, Tom, if you could build on that, from system design perspective, when engineering an ozone system, how do you determine what needs to be measured and where do those analyzers should be placed? I know Ron has a couple of options, but what's the deciding factor between all of that?
The most important factor is placing the analyzer for the ozone gas production side, which is inside the enclosure for the quad box systems, what we call our 5-up, 10-up, and so on, the Zenith systems. All of them will have the BMT high concentration analyzer inside there. That will always be there. We always have that. It's a very important part, a vital piece of the equipment in determining the production efficiency of the generators. So there's always will be a BMT analyzer inside an enclosure in our Pinnacle systems. This is extremely important because in the past, in the early days of ozone, really didn't have an analyzer like that size, that quality of analyzer that BMT makes back in the early 90s and early 2000s, actually. We went through a number of things. When I started out with Guardian and then Pinnacle, I actually introduced the need for ozone analyzers in our systems to confirm production, to know how much we're producing, to say, yes, we are making now 100 grams an hour of ozone at this percent by weight. When I got into contact with BMT way back then, I recognized the engineering, how well engineered they were, and the design of them that were well suited for our enclosures. So they're very important these days. We often will have what's called the FAT, or factory acceptance testing, done for our systems, where our clients require us to show and demonstrate that these generators will produce 1,000 grams per hour of ozone at 10% by weight, for example. And we'll produce that at a certain amount of oxygen flow, gas flow, temperature, and all that. And so having these analyzers in there in our production is extremely important. They also give us information in terms of not only grams per hour output, but also that we modulate our systems, the power to our systems, based upon the percent by weight. So we actually use them to produce a consistent power input, or a consistent oxygen ozone concentration. In other words, when we put our systems together, we typically design it to hold at 10% by weight on the larger systems, and then we modulate the actual oxygen gas flow to change the grams per hour output. That way, we have a consistent ozone concentration going to our injection skids. And that helps us downstream with engineering in terms of mass transfer efficiency, what we're looking for in terms of the KLA involved with the venturi and the dissolution of gas and so on. Sometimes we will have some systems where we'll do the off gas, like Ron was saying, where we're looking at the off gas from a header. And this is important because in some systems, they really do want to know dynamically what that percent mass transfer efficiency is. And in order to do that, we have to look at the off gas, what didn't get dissolved, what left the reactor, what left the chamber in terms of off gas. And that information is really important because then we can bring that back into our MLCP and HMI and then calculate, yes, you are getting 93 or 95% transfer efficiency of those. The system's running appropriately. And that information can be very, very important, especially in larger systems where they're really looking for that efficiency and want to confirm that efficiency. Of course, the ambient level is always going to be there as well. I guess I'd say that's the second most important piece of equipment is the ambient ozone, like Ron was showing. It's for safety levels and for OSHA, kind of safety for ozone in a workplace or an enclosed area, to always monitor the background ozone in those areas for make sure there's no leaks and there's any ozone in the atmosphere, and of course to limit any exposure. And all our systems are designed to interlock with that, and they give off a low level alarm if there's a certain percentage of ppm by volume ozone in the workplace, and then if it gets up to a certain point, a high limit, it will shut the system down and send out an alarm to operations. So I think those two are the most important. The BMT high concentration and the ambient ozone monitor are the two most important pieces that we use most often. It is true that on occasion that our clients want to confirm that the vent gas, like Ron was saying, that's coming out of the destruct unit is indeed performing 100%. And in some cases, we will have that as well as additional level of safety. But I have to say that knowing the concentration of ozone coming out of the generators in real time, efficiently and accurately is a game changer. And it's certainly a key piece of equipment for us in knowing what we're doing and how we're dosing our systems. Not only is it important in terms of ozone efficiency, but we actually will use that number in my engineering. I'll use the grams per hour output with a certain calculation for mass transfer efficiency to determine the dose in the processed water. So we actually have that calculated on the fly. So we have the flow rate coming in, so many gallons per minute, how so many grams per hour of ozone being produced, which is calculated from the BMT, along with the oxygen gas flow and some algorithms and some calculations to come up with that number. And then with transfer efficiency designed in our system, 93, 95% transfer efficiency, we get our transferred ozone dose. Or sometimes we'll just use applied ozone dose, depending on what we're doing with the calculations. And we'll use that a lot to determine two things. One, the client has the option to use a fixed dose algorithm. In other words, they can say, I want to just dose 10 milligrams per liter of ozone. And maybe my flow rate will vary somewhat. So you just put 10 milligrams per liter in your PID and your set point, and the generator will hold that 10 milligrams per liter all the time as a dose, meaning it's calculating it on the fly from the BMT, from the oxygen concentration and flow rate, to give that dose all at the time with a nice smooth curve. Sometimes it's a fixed output. Sometimes the client wants to know, I just want to generate 500 grams an hour. That's it. Then again, we're using a BMT analyzer to measure the output from our generators, and our generators will give 500 grams an hour consistently, no matter what. The third part is we'll use the BMT analyzer to calculate the applied ozone dose. And in some systems, especially when we're doing peroxone or hydroxyl radical production, we'll use that dose calculated to go into water for a transferred ozone dose, let's say 5 milligrams per liter of dissolved ozone transferred into the process pipe. And then we will dose hydrogen peroxide based upon a certain mass-to-mass ratio, based upon that transferred ozone dose that we calculate to dose the right amount of hydrogen peroxide to create hydroxyl radicals. So it's a very important piece of equipment that we rely on for a lot of parts of our engineering and ozone process control.
Oh, thank you so much. So, Ron, talking about that, from your experience in the field, what are the risks of not having accurate ozone measurements? How does that impact the system performance, compliance, any operational costs? What have you seen in the past?
So I think the return on investment for accurate measurement really comes from cost control. And then probably risk reduction, right? So Thorin was talking about, it'd be expensive to make ozone, and overproduction or overdosing is just wasteful. So if you don't have accurate measurement or no measurement, you're left with producing much more than you really need at a cost for lots and power that maybe isn't sustainable, but is obviously unnecessary, right? So underdosing comes with other risks, right? So you're given, as Thorin was just talking about, project goals that he has to meet. For disinfection, I think of what is the danger of underdosing? Well, you're going to leave the residual TOCs, right? There's typically secondary systems in place to catch underperformance, but that's unnecessary. With accurate measurement, you know exactly what that performance needs to be, and you're providing that performance or measuring it accurately going in, then you can be more assured that you're meeting your project goals, right? There's other things. If it's being used for taste and odor, think of inconsistent delivery, customer concerns, right? For wastewater, could be environmental considerations for underdosing, right? Where you might have some kind of punitive impact if you're releasing effluent that's not meeting your environmental target. So, from a return on investment, instrumentation is somewhat expensive to put in, but necessary up front and pays for itself over time because you can dial in the exact control that you need. And then maybe lastly, we've touched on it, but safety, if you are working with ozone, there are exposure limits that are defined by OSHA. And so you need, this is more under the heading of monitoring than it is on measuring, but you also need to monitor a facility that is being used, that has an ozone system.
And so, Tom, once you have these reliable measurements in place, how do the analyzers tie in? I know you spoke about it in the last question, but how can you discuss the feedback loops, the PNIT control? How do you see this taking place?
When we get the measurement, like Ron said, it's a small flow rate, 0.3, 0.5 liters per minute, coming out of the main flow that's being measured in real time. So when we take that information, let's say it's running near 10% by weight, which is around 145, 147 grams per normalized cubic meter or thereabouts. That number that comes out, which is in terms of grams per normalized cubic meter, is set at standard temperature and pressure. We actually calculate, make sure those values are apples to apples in terms of what we looked at in our gas flow. So our oxygen flows are also standardized, because with gases, as you know, pressure and temperature has an impact on that due to compression and densities of gas. We take that number in, those two numbers, with some density calculations, come up with grams per hour, because you have liters per minute are converted to meters per minute, for example, or meters per hour, depending on the units you want, and then you just multiply that by grams per normalized cubic meter, and you'll get grams per hour. There's some other algorithms inside that, but that's basically it. That number then is fed into our HMI, and then depending on what we're doing with it, it could be just an output for recording and saying your system is producing as expected. It's also logged so that we know how much the unit is producing over time, depending on your process as well. And that number is, like I said before, used for different purposes. If you're using in our sensor mode, if we're saying I want to have, like I was saying earlier, I like to dose this stream at a specific applied ozone dose, just make a number, 5 milligrams per liter in your process stream. Well, then by calculating from the flow rate that we have an input flow rate from a meter, so we know the flow, get that liters per minute, then with the grams per hour output, we can modulate the power to the generator so that the grams per hour calculated and divided into liters per minute, you'll get your milligrams per liter dose. So you just do some math on that. Well, the system will modulate the power into through a PID to meet that criteria. So if I only need 150 grams an hour to make 5 milligrams per liter at this dose, then it'll hold it to that. If the flow rate goes up higher, then I need more ozone. The generator will increase the power output to meet that criteria based upon the grams per hour coming from the BMT. Calculate it to make sure I get my 5 milligrams per liter consistently. So that's one very important way that we use it. Mm-hmm. The other one, which I had mentioned before, is that in some systems, when we do peroxone testing, which is making hydroxyl radicals with hydrogen peroxide, we'll use the grams per hour output to calculate the applied ozone dose, like I was saying earlier, like 5 milligrams per liter, and then the amount of peroxide based upon a certain mass-mass ratio will be injected to meet that. And so that we're getting that continuous dosing going on with the system. That's one of the main ways we do it. The thing I wanted to say that's important, not only in terms of production and systems in the real world, I use the BMTs in my lab for so much of the research that I do. It's critical to what I do. As a segue, I do ozone demand decay studies in the lab, and one of the studies I do is using ozone gas injection. Some say it as batch or semi-batch, but basically is what I do a demand study where I think the ozone demand is going to be higher than 10 milligrams per liter in my sample. Doing that by a liquid injection, there's too much dilution occurs. So when it's a high concentration sample where I need to do 10, 15, 200, even 1,000 milligram per liter dose, I use gas injection. And in gas injection, I actually use 2 BMTs to do that process because I do exactly what we're talking in the big systems. I have a HMI system set up with a PLC with all the programming where I look at my ozone output. Maybe I'm doing 2 grams an hour. It's a small system for a small sample. And I'm measuring that output continuously. And then when I inject it into my reactor, I'm measuring the off gas from that reactor to see what didn't react. And maybe I'm getting 1 gram per hour coming out. So that's 50% mass transfer in that reactor, and I accumulate that over time, to put it really, really simply. And with that system, I can very accurately quantify the ozone dose within that reactor for the studies that I do. And having the BMT analyzers is critical for that. I've done in the past also a lot of research on mass transfer efficiency. So using the analyzers to determine exactly what my mass transfer efficiency is based upon certain hydrodynamic characteristics, meaning when I'm doing some flows like pressures of Venturi's, pressure drop, gas-liquid ratios, contact time, different ozone mass transfer devices. I use all that in my lab to determine what that true transfer efficiency is, to determine, okay, yes, that's actually efficient. That's a 90%, that's a 95%. These criteria, these engineering parameters are correct, and this is what we'll design in our systems.
Thank you, Thorm. So Ron, for some of the most common mistakes you see in the ozone industry and ozone measurement, could you touch base a little bit on what you see in the industry?
BMT instruments themselves are fairly bulletproof, and there's quite a bit of self-adjustment and automation built into them. So what I've experienced is common mistakes tend to be misinterpreting data or just errors in the field. So for example, the instrument itself will display a problem. It'll give you a warning if there's some kind of a problem, a cuvette dirty or something like that. Customers will get a high lamp warning and assume there's something wrong with the lamp. Now, BMT's UV lamps are the best in the industry, without class. By far, they will last the longest of any lamp out there. However, because of that, I think many clients believe that the lamps are too fragile and they won't last that long, mostly because our competition maybe gets a couple of years out of a UV lamp. Okay, so the warranty on the BMT lamp is 5 years. So we know it's not a lamp problem when we see a lamp high error. Typically what's happened is the instrument has been subject to some kind of fouling event, and the internal diagnostic, it's recognizing that the cuvette has been fouled and it's trying to drive the lamp voltage higher, hence the lamp high error, to compensate and increase the intensity of the UV to the photodiode. Okay, now in some cases they've been fouled too much and it can't go past the upper limit of the voltage, and that's when you get the lamp high error. Okay, so that's a common mistake of misinterpreting data. Normally they will get phone calls and we talk people into a better understanding of that kind of thing. The most common cause of service, especially on the high cons, is some type of fouling. Okay, so by the nature of the UV photometry is assuming that the only thing in the cuvette is ozone and oxygen, maybe some trace noble elements, some nitrogen or something like that. So if, for example, there is a problem with keeping your system dry, your source oxygen has too much moisture in it, and it's mixing with ozone, what do we get, Thorm?
Nitric acid.
Nitric acid, yeah. And so if there's a control problem in the system, the high concentration ozone analyzer is always the lagging indicator of a problem upstream. Okay, so that's the most common thing we see, and that's the most common reason they come back for service, is because they have been fouled. Okay. The other, I would say, common mistake, maybe not a mistake, but some piece of advice that people don't always follow. When they take an instrument ozone generator offline, the analyzers are always on. And so depending on what happens when the ozone generator goes down, is there no flow of air? Is there a flow of oxygen through there? Is there a potential backflow, inducing moisture? Those types of, again, this could go under the heading of troubleshooting. Those are the types of things that people will do. They take a generator offline and they ignore the analyzer. We recommend to take the analyzer sample gas stream out of service. I don't know that that's necessarily a problem. I've never experienced that with Pinnacle products, but it is fairly common in some larger installations to leave that line open, which I think can cause more rapid fouling because it's something other than oxygen and ozone that's going through the cuvette. Okay. In some installations, they don't dry the off gas before sampling, which I've already kind of described. It can create problems with either condensation on the windows or fogging of the windows, which affects measurement and becomes a long-term problem for the instrument as well. With ambient ozone monitors, specifically safety monitors, we find they're always running in the background and they're happy and people ignore them and they forget they're there. And so there are things like washing walls or solvents or something like that in the area where they're doing a sampling and then suddenly sucking moisture through the instruments. So, from a best practices before cleaning occurs or painting or use of solvents, take that analyzer offline. And the other common thing that I see from a field perspective is on a bent gas ambient ozone analyzer, they have particle filters that should be installed at the sampling point. And often they're either not installed at all, no filtering at all, or they're installed at the analyzer itself. And it's vent gas, so there's fine particulate dust that can collect along the path, the sampling path, if the filter is not there at the point of sampling. So what is that dust? It's Carolite 200. What does it do? It destroys ozone. So what would be the effect on the ambient ozone analyzer? Well, it'll reduce its response rate because you're destroying ozone along that path, right? As I said, these instruments are pretty bulletproof and they self-monitor. And so most of the mistakes I see are just from an installation or a maintenance perspective, not changing filters in a timely fashion, that type of thing, which results in false alarms.
And Tom, is there ways that we can actually avoid this during design phase?
Yeah, and I think that the main thing is what Ron was going to allude to, especially on our high concentration ozone analyzers, is making sure that they're sealed properly, that they're only getting the gas that's coming from the generator, and ultimately it's really upstream, which is important for not just for the analyzers but for the generator itself. And so our quad blocks are, warranted, for 20, 25 years, but that's predicated upon good gas quality. So really, if the gas quality is maintained upstream as designed, and that's really the most critical point, because everything's sealed. Right. So once it's moved through, it's all sealed, hermetically sealed in a sense. As long as that gas quality is maintained as by design, which is what we put a lot of effort into, either from oxygen concentrators, making sure there's proper filtration between the air steps so the fine dust with zeolites doesn't get into the system, or the locks, it's properly clean piping and all that. As long as that's taken care of, a gas quality coming into the Pinnacle blocks is meeting our specs. It almost certainly will meet the specs for the BMT analyzers. So that's really by downstream that we maintain and protect the BMT analyzers on the high concentration side, for sure. In my lab, I do a lot of strange things in my lab, and I do have a tendency to coat those optics, but that's because I'm doing, very different things like high VOCs, land leachates, or, things that are giving off gas, and I do have to clean those at times, and I etch them. But that's like really harsh environments that I'm working with on those.
Thank you, Tom. So, Ron, to close this out, if you had to provide one piece of advice to engineers, operations about ozone monitoring, what would that be?
So 95%, I think, of all service requests that come into our shop really come from poor maintenance or preventative maintenance practices at a facility. So Kerwin Rackness and James Murray published a paper in Ozone Science and Engineering that spoke about the importance of keeping generators cool and dry, and really the system impact that, like what Thorum was just talking about, upstream, if it doesn't. My advice is that every plant operator or engineer read this paper because it really reads as the best practices of what to do and what not to do. And we have a PDF copy of that. We send that out to facilities liberally when we think that they're having problems. So from a measuring and monitoring perspective, if the entire system is well maintained, you can trust the data that are coming from your analyzers, okay? And you really need very little preventative maintenance to keep them running and happy for a very long period of time.
I like that. And one of the things I do find in the field that we have to make sure to get the good data is that the sample gas is flowing through the BMT analyzers. And it's kind of funny. It's a simple thing. But I've had it where the pressures are a little off, especially in certain ozone pilots. And when you get a funny number, like, wait, power's not changing, something like that. Most often, 99% of the time, is because the sample gas flow, the needle valve was too closed, or something was preventing the gas flow going into the BMT analyzer. And that's the first thing I always troubleshoot and check, and make sure that I get that 0.3 to 0.5 liters per minute flowing through the BMT analyzer. And once that flow's flowing, then all of a sudden everything's working out perfectly.
So thank you both. This has been a great discussion, one of the most important aspects of ozone system performance and one that often doesn't get enough attention. Ron, Tom, thank you so much for sharing your experiences and insight. And to everyone watching, thank you so much. If you'd like to learn more about ozone systems monitoring and optimization, please feel free to reach out to pinnacleozone.com or OSTI-inc.com. Thank you again for joining the Pinnacle Academy, and we'll see you next time. Thank you.